Dear students, in the previous sections we have discussed about Kirchhoff's laws, and it is very useful. The Kirchhoff's laws are very useful to analyze complicated electrical circuit. The first law, known as the junction rule, it states that the algebraic sum of the currents meeting at a point is zero. That means in an electrical junction, the incoming currents are taken as positive and the outgoing currents are taken as negative, and their algebraic sum of the currents meeting at a junction is zero. That means the total incoming current is equal to the total outgoing currents. The second law, that is known as the loop rule, it states that in any closed circuit, the algebraic sum of the products of the current and resistance of each part of the circuit is equal to the total EMF in that circuit. That is the sum of the products of I into R, the products of current and resistance, is equal to the total EMF present in that loop. And we have seen the examples for the application of these laws, and also these Kirchhoff's laws, this can be used to find the balancing condition of a Wheatstone's bridge. So what is the Wheatstone's bridge? Wheatstone's bridge is a network of 4 resistors commonly used for the measurement of resistance. So you can see in the figure, it represents a Wheatstone's bridge. We are going to apply the Kirchhoff's laws to find the unknown resistance in the Wheatstone's bridge. In the figure you can see there are the 4 resistors, out of which P, R and S are the 3 resistance boxes, and the value of resistance we know, and X is the unknown resistance whose value has to be determined. And a cell of EMF is connected between A and C, and a galvanometer is connected between A, B and D. That is the circuit diagram. When the circuit is switched on, the current flows through the circuit. So at the point A, the current coming from the source of EMF is split into the 2 currents. One is I1, which is going through P, and I3 is going through R. At the point B, you can see it's again split into 2. So I1 is split into I2 and I3. Here I2 is going through X, and Ig, which is the current going through the galvanometer. And look into the junction D. Here I3 is a current coming to the junction D, and also Ig is also coming, but I4 is going out through the resistance S. And at the junction C, the I2 and I4 are combined and is going to the source of EMF. Now we are going to apply the Kirchhoff's laws. Before that, we are taking the suitable resistance in P, R and S, and we know X is the unknown resistance. And by analyzing, or we are applying the Kirchhoff's laws, first apply the junction rule at the junctions B and D. So at the point B, I1 is the incoming current and I2 and Ig are the outgoing current. So I1 minus Ig minus I2 equal to 0. That is equation number 1. And at the junction D, I3 is coming and IG is coming and I4 is outgoing. So I3 plus IG minus I4 equals 0, equation number 2. Now let us apply the loop rule to the closed circuit A, B, D, A and B, C, D, B. Let us first apply the loop rule to the A, B, D, A. So the products of current and resistance is equal to the total EMF present in that loop. Now the clockwise direction is taken as the positive direction and anti-clockwise taken as the negative direction. Okay. So on the first loop here I1 into P, that is positive, that is the current is in the positive the clockwise direction. And there is another element, that is capital G is the resistance of the galvanometer, then Ig into G, that is also again taken as positive. And third element is I3 into R, that is taken as negative. So I1 into P plus Ig into G minus I3 into R equals 0. That is equation 3. Similarly, we can apply the loop rule to the loop BCDA. BCDA. Here I2 into X positive, while I1 into S and Ig into G are taken as negative. So I2 into X minus I4 into S minus Ig into capital G equals 0. That's equation number 4. Now we are going to adjust the values of resistance in the resistance boxes. Either one or more of the resistance in the boxes can be adjusted until the galvanometer shows no deflection. That means we are making the value of Ig 0. Okay. Then what happened to the equations 1, 2, 3 and 4? Here we are making the Ig 0, that is current through the galvanometer made equal to 0. Then this condition, we say that the bridge is balanced. The bridge is balanced. Okay. Now we are going to find what are the relations between the 4 resistance in the balanced condition. So let us substitute Ig in equation 0. Ig equal to 0 in equations 1, 2, 3 and 4. Let us see first one. Making Ig equal to 0, the equation 1 becomes I3 equal to I2. This is equation number 5. And the equation 2 becomes I3 minus I4 equal to 0. From that, I3 equal to I4. That is equation number 6. Now let us move to the equation number 3. I1 into P plus this part becomes 0. So minus I3 into R equals 0. So I1 into equals 0. So from that I1 into P minus equals I3 into R. That's equation number 7. Similarly, equation 4 becomes I2X minus I4S equal to 0. From that I2 into X equals I4 into S. That's equation number 8. Now let us divide equation 7 by 8. On the left side, we have I1 into P by I2 into X equals, on the right side, I3 into R divided by I4 into S. But from the equations 5 and 6, we can see I1 equals I2. So on the left side, these two current is cancelled out. On the right side also, I3 and I4, I3 equals I4. So that currents are also cancelled out. Then the relation becomes P by X. P by X equals R by S. So this is the relation between the 4 resistance in the state of the balance. So this relation is called the balancing condition of a Wheatstone's bridge. This principle, so if we know the values of P, R and S, then the unknown resistance X can be calculated. For that, first we have to make the bridge balanced. So in the balanced condition, we have the values of we have denoting the values of PR and S. Then substitute in the balancing condition, the unknown resistance X can be evaluated. So this principle is used in resistance measuring devices like meter bridge. For the purpose of resistance measurements, the Whetstone's bridge is constructed in several forms. One of the common forms is the meter bridge. So this is a typical diagram of the meter bridge. It consists of a uniform resistance wire AB of length 1 meter is stretched on a wooden base parallel to a meter scale. So from the figure you can understand this is a 1 meter length wire and it is kept parallel to a meter scale, and we have some of the copper strips. We have two L-shaped copper strips, and here is the two L-shaped copper strips, and a straight copper strip are fixed on the wooden base. And then we have the two gaps. Okay, here is one gap and this is another gap. So the strips are provided with the terminals to fix the connecting wires. Now a resistance box, capital R, and the given resistance wire X are connected in the gap. Here the X is connected in the left side gap, and the resistance box, capital R, is connected in the right side gap. And a cell of EMF E is connected between A and B along with a key. And a galvanometer, capital G, is connected between the central terminal, and that is C, and a jockey J, which can be slide along the wire. From in the figure you can see the galvanometer is connected between the one end of the galvanometer is connected to the central terminal C, and other end is connected to a jockey which can be slide over the resistance wire. Now this is our arrangement. Now we can do the experiment. A suitable resistance, capital R, is introduced in the resistance box. So then the jockey is moved along the wire to get a null deflection. So that we have to move the jockey from the terminal A slowly. Then you can see the galvanometer shows a deflection on the one side. So when we move from the point A, we can see that the needle in the galvanometer coming towards the zero position, and at a particular position and a particular point, what will happen? The galvanometer shows null deflection. That means the needle reaches the zero value. Okay, so let Lx be the balance. The Lx be that length of the wire from the point A. Now it is called the balancing length. Now we can measure this balancing length with the help of the meter scale. Let small r be the resistance per unit length of the meter bridge wire. That means small r is the resistance per unit length of this wire. Then we know the total length is 100 centimeter. So according to the Whetstone's principle, so when we apply the Whetstone's principle, we have to know what are the four resistance. Here one resistance is X, that is unknown resistance, and another one is capital R. And what are the other resistance? The other two resistance are the resistance for the length, the Lx, and that is the resistance corresponding to this resistance wire from the point D, and the fourth one is the resistance wire, the resistance corresponding to the length of the wire from the point D to B. Okay, let RS, let small r be the resistance per unit length of the meter bridge. Then the resistance for this portion is Lx into R, and the resistance corresponding this portion, that is 100 minus Lx into small r. Okay, now we have the four resistance, and now the meter bridge is a balanced condition. The galvanometer shows the zero deflection. That means no current is flowing through the galvanometer. Okay, now we can apply the balancing condition, and we can write the relations between the resistance in the network. So we can write X by R equals the resistance corresponding to this portion, that is Lx into small r, divided by the resistance corresponding to this length of wire, that is 100 minus Lx into small r. So the resistance per unit length can be cancelled out. Now X by R equal to Lx divided by 100 minus Lx, or X equal to Lx into R divided by 100 minus Lx. Now we can repeat the experiment by changing the gap. That means we are interchanging the X and capital R, and then again we measure the balancing length as we done in the previous case. Here now the balance length is measured from the point B, because the unknown resistance X is connected in the right gap. So we have to measure the balance length from the B. Okay, and that means for a given resistance capital R, we have two balance length. So we have to take the average value, and we can substitute this average value of Lx in the above in this expression, and we can find the value of X. So for a given value of capital R, we are taking two values of balance length. Now the experiment is again repeated by changing the value of capital R. So in the first case you can take, if you are taking 2 ohm in the first case, in the next trial you can take 3 ohm or 4 ohm. Okay, then we can take the readings, the two balance length for each value of capital R, and in each value of capital R we can measure the value of unknown resistance. So we can take the average value of X, that gives the balancing, that gives the resistance of the material. Now we can also find the resistivity using this experiment. And if we know the radius, the radius of this wire, the resistance wire, we can measure by means of a screw gauge. So if we know the radius of the wire and we know the length of the resistance wire is, now this one, the length of the resistance wire is, the length of the unknown resistance wire is, we have to measure if it is capital L, that we can measure with the help of a meter scale. Then the resistivity rho can be calculated using the formula rho is equal to X into A divided by L. Here A is the area cross section of the unknown resistance wire. So if a small r is the radius of the unknown resistance wire, then its area cross section is pi r square. So we can calculate the resistivity or the specific resistance of the material of this unknown resistance. Rho is equal to capital X into pi r square divided by capital L.